All right, let's take a look at this slide. A couple more slides at the end of this section. And so the way we do it in a calculator, we're given the answer already for the confidence interval. But we can kind of go backwards and say, what if somebody gave us a confidence interval and we want to know what our point estimate is, and we want to know what our margin of error is? So all it would take is a couple of simple formulas. It would kind of make sense from a number line point of view. That if you have a number here and a number here, you can find out this number in the middle by just finding the mean, right? And that's what this is. This is the mean of those two numbers. It's going to give you the middle value. Now, this margin of error between two numbers, if you take the difference between those two numbers, you would get that length of that interval, and if you take half of that difference, you would get the margin of error that they would be looking for. So if you didn't know these two formulas, and you can work your way through, you can picture the number line, and you picture the upper and lower estimates, or the upper and lower confidence limits, then you can probably find the middle, and the number in the middle, or you can find the length from the middle to one of the sides, which is essentially what you're doing here. But these two formulas kind of give it a more compact formula for you to try to remember. If you were doing the things by hand, then along the way you would know what p hat is, and you would know the margin of error, because that's the process that you would take in finding your confidence interval. But the way we did it with a calculator, we didn't know what the margin of error is from a calculator. So I think these formulas might be important if you wanted to try to do it from a margin of error approach. So what I did in the next slide is I took that example that we actually did, and then all I have is a calculator command, or the calculator results that give us the answer. So let's say this is our answer. Say in the test situation, you were asked to find the confidence interval for this situation. You found the confidence interval. And then the next question is, based on your confidence interval, what is the margin of error, for example? Well, if you look at what the margin of error means, you got 0.476, 0.544. You can probably figure this out, right, by finding the mean, or you can just say, oh, that's 51%. But if you're looking for the margin of error would be the length of one of these sides. So a couple ways to find it. We can subtract these two things, but without even introducing this, we can find that margin of error by using the formula that they have, which is to find the difference between these two things, 0.544 minus 467. 476. Oh. 476. And then that would be the distance of that whole interval, but if I want just half of that, I'll divide this by 2. And if you do this correctly, you should get, what is it, 0.034? Yeah? Which is the margin of error that they had found earlier. So it's just another way to look through it. Okay? All right, now, that we know about confidence intervals, we know about point estimates, we know about critical values and margin of errors and stuff like that. The next section, we'll be doing exactly the same thing, except we'll be doing it for a mean. So, we'll see how fast we can go. We're going to fly through this one. Before we fly through this one, they broke down the idea of finding the mean or estimating or finding the confidence interval for a mean with the two paths here would be if you know the sigma, the population standard deviation, and then the other path would be if you don't know sigma. Turns out that if you don't know sigma, then we're a little bit more trouble here, and we're not going to be able to rely on the standard normal distribution anymore. And so what they do is they introduce another distribution. We'll see that in the next section, but we'll see how fast we can get through this one first. Okay, we'll just skip through this stuff. Maybe just underline the idea that we should know the standard deviation for these things. And we'll get to the requirements. Oh, right here. So the requirements for the process in this section would be, the requirements are always going to be the sample is simple and random. We always want a simple random sample. If we don't have that, then all the stuff can just get thrown out the window because there are some biases here that take this to a different level. So we're always going to want our sample to be simple and random. The second one is the population standard deviation is known. Now, this is kind of silly because if you don't know the mean, right, and the whole reason we're doing this, we're estimating it because we don't know what the mean is. We don't know what mu is. And for some reason, we're supposed to know what sigma is. So this turns out to be, this section turns out to be not very practical in a real life situation. Let me point that out here right now, not practical. Practical. Because if you know what sigma is, chances are you would already know what mu is, what the mean is. So just for the sake of the statistics, the subject of statistics and where this is all based on sampling distributions and stuff. I think it's good to walk through this exercise where we'll just assume that sigma is known. But in real life situation, we're going to use something else. And then here they talk about another condition saying that your population is normally distributed. Now the central limit theorem didn't really ask for your original population to be normally distributed. But in this case, it's making sure that your population is normally distributed. Or you have a sufficiently large sample size. So I think these requirements are important to set aside and just have on a sheet of notes ready for you to look at or find really quickly. They do ask you some of this in the homework to make sure that it's all satisfied. All right. So the best estimate for your population mean mu is your sample mean sigma, or not sigma, your sample mean x bar. Just like p hat and p, it just makes sense, right? You wouldn't use your standard deviation to estimate your mean. That seems kind of silly. And this is one of those things that was obvious back then. It's just recurring as your point estimate. Okay, so we're going to use x bar as our base point, and then when we construct a confidence interval, there'll be x bar plus and minus your margin of error. I'm going to skip over this stuff. So here's I don't know if anybody's studying to be a nurse around here, but what's the normal temperature for the human body? 96? 98.6, right? Or, so, yeah, Celsius. We'll stick with Fahrenheit. So the average body temperature is supposed to be 98.6. But it turns out that in Minnesota, people are a little colder there. A study found the body temperatures of 106 healthy adults, and the sample mean was 98.2 degrees. And sample standard deviation was 0.62 degrees. These are all in Fahrenheit. Find the point estimate to estimate the population mean for all body temperatures. Now, they didn't say this is from Minnesota, but our author is from Minnesota, so this is probably the adults from Minnesota. But they're trying to generalize to all the country, so that's a bad sample. Anyways, if we're just to stick with Minnesota people, then the average body temperature for all Minnesotans would be, based on this, would be 98.2. So that's your best point estimate. Now, of course, you want to, when you're finding, estimating a value, you're estimating it using an interval, and so we're going to eventually create a confidence interval. But for that one single point or one single value, that single value estimate would be 98.2. All right, let's get a little bit more interesting here and take a look at the margin of error. So this is the same definition that they give, except they change the p hat and the p with x bar and mu. So the margin of error is the maximum likely difference observed between the thing that you're estimating and your point estimate that you're giving. So the thing that you're estimating is mu, your point estimate is x bar. So the difference between the population proportion and the sample statistic is going to be your margin of error. So we need to come up with a formula for that. So it's also going to involve a confidence level, so we're probably going to need the z sub alpha over 2 business again. And then it's going to involve something else that doesn't have p hat or q hat, because we don't have p hats and q hats here. So we're talking about means and standard deviations and stuff. We're not talking about proportions. So what are they going to do for us? I don't know if this sigma divided by square root of n looks familiar. This came from the central limit theorem as our standard error of estimate. Sigma sub x bar. So we are working with x bar and trying to find out if x bar, how close x bar is to the mean. And so this is the standard deviation for all those samples of the same sample size n. And we're basing it on your confidence level, the z sub alpha over 2 that we found. So see how that's a little bit different? So this is a little bit different from the square root of p hat, q hat divided by n business. And now we just, but the z sub alpha over 2 is still there. Okay. As long as we're dealing with the standard normal distribution, we'll use these z critical values. So now that you know the margin of error and you know your point estimate to be x bar, then your confidence interval would just be x bar plus or minus the margin of error. And I like this notation over here because you're forced to, I'm forcing you to tell me what the population parameter is that you're testing or that you're finding the confidence interval for, and that is mu. So you notice the other two don't have mu in it. The first one has mu because it's testing for the population mean, and so I like to see that. So it's the same setup as before, right? Same setup as before, except we have different variables, different formulas. So without writing and going through all the stuff, we just, the procedure for constructing, you want to verify those conditions are satisfied, the requirements. You find your z sub alpha over 2, you find your margin of error, you add and subtract your margin of error from your point estimate, x bar, and then you write it like an inequality. And then you round off using the round off rules, and the round off rules would be 1 decimal place past the thing. So it's the same as the descriptive statistics that we've had before, 1 decimal place past the original data set, if you have the original data set. So in the homework, they always tell you how far to round off. So this is a bit of a big mess over here, but let's see if I can make sense out of this for you. So this is the original problem. And so the first thing we want to do is we want to collect information that we're given from the word problem. So that's one of the things that we need to do with word problems is look at it, read it, and see if we can pull out all the relevant information. We know that 106 is your sample size, and they gave us the sample mean. And then now it's important that when they say the standard deviation was given, it's 62.62 degrees. And so one of the things about this problem is that they have the sample standard deviation. So based on what we've read so far in the problem, we don't have the population standard deviation. Okay, so already this shouldn't be the technique that we're using here. But they end up assuming, and that's a big assumption, assume that sigma is equal to 0.62. Sigma does not equal to 0.62 in this problem, but they are assuming that it does, just for the sake of using this technique. Okay, because in reality it's hard to figure out what the population standard deviation is. So 95% confidence, you have your critical value to be 1.96 again. And now that we know sigma, or at least we're assuming the sigma is equal to 0.6, and we know that the sample size is 106, then our margin of error formula gives us 0.12. So from then on, you just take 0.12, and then you add and subtract it from your 98.2, and then this is, I don't know why they wrote this first, but this is your final answer. Still doesn't go up to 98.6. So that's it. This is how they would get it using those 5 steps and stuff. They skipped over the first step about checking the requirements to make sure it's all correct. But this is how you would get it. So the next slide would be the interpretation of this thing. This is our answer. Based on this answer, what can we say? Well, we can say that we are 95% confident that the real population mean falls between 98.08 and 98.32. So again, this doesn't cover 98.6. So based on this study, he seems to be convinced, the author seems to be convinced that the body temperature should be adjusted down from and 98.6. Okay. Now let's use our calculators to do this. So all I'll do is I'll take the problem, I'll take this problem and put it on another file. And we also need to assume, and we'll make this assumption here, assume sigma is 0.62. All right, so let's take out our calculators. And all these inferential statistics is going to be under stat and test. So stat and test. And this first one is the first one, the z-test. This is a z-test. This is using the standard normal distribution. And the first thing they ask for is the input. Do you have data? Do you have data in L1 that you want to test? Or do you have the sample statistics already summarized for us? In this case, oh, I'm sorry, not a z-test. Z-interval, sorry. Let's try that again. Stat, test, and z-interval. The z-test is next chapter. Okay. Again, the first thing they ask for is the input. Do you have data in L1, or are we going to use sample statistics? Well, we're going to use sample statistics. And the first thing that they ask for is sigma. What is sigma? You're using the z distribution here, so you must know what sigma is. And so in the original problem, we actually didn't, but we're just going to assume at this point that sigma is 0.62. Now, what is the sample mean that you found for your study? Well, I think it was 98.2. That's what x bar was equal to. And what is your sample size? The calculator is asking. Say it's 106. You're doing a confidence interval. What's your confidence level? Turns out that if you put 95 and you forgot to put the decimal there, that should also work okay. So you put in those values and you hit calculate, and then you're going to get your answer rather quickly. And pretty much the same as the other one. So there it is. And the only other step that I'd like you to take is to write it in that interval notation. So the interval notation, I think, was 98.08 less than mu less than 98.31 or 32. Let's put 1.8. And then, of course, you want to write this in words. So in words, we can say we are, 95% confident that the true mean is between 98.082 and 98.318. And these are in degrees, so just add a little degree symbol here. And then that's it. That's what I would be looking for this type of problem. Okay? So the same business. If you know the the interval limits, and I decide to ask you what the margin of error is, you just take the difference and cut it in half, just like we did before. So can find margin of error. Just the same way we did before, by taking the difference, 98.318 minus 98.082 divided by 2. And the margin of error should be pretty much like what they had before, which is 0.0, what is it? Zero what? Zero 1 2, or no, not 0 1 2, 0.12. If they ask you for the margin of error. Okay. All right, any questions about doing these problems? We're easy with a calculator. And Frank, when he gave his little spiel over here, he talked about getting frustrated with a calculator, doing your homework, and if you don't know how to use your calculator, you'd be going through all this mess over here, trying to keep track of stuff. And the more mess you have, the more chances for error. You make one little mistake here, you don't get 0.12, you get 0.15, and now all of a sudden you're not getting the right answer. And go back and redo everything over, and it's a big mess. So use your calculators. Okay, the next topic is a sample size. They didn't do that dramatic where did this formula come from business, but if you remember our margin of error formula, z sub alpha over 2 times sigma over the square root of n. If you were to solve for n using algebra, you get n is going to equal to this thing. So now you have a formula for estimating the mean. Now, when you're finding a sample size, you want to do a study, you want to know how big your sample should be. You're going to set your own parameters for your degree of your confidence level and your margin of error. So the other weird part, just like we had a p hat in that previous one, who would know what p hat was? Well, if you had a previous study, maybe. Well, that's the same business with sigma. What's sigma? Sigma is the population standard deviation, but if you know that already, then you probably know the mean and you wouldn't go through this stuff. So practically, you're not going to know what sigma is. So you're going to have to do some guessing on how to create sigma or how to come up with sigma. And we'll talk about that in a few minutes. Let's see if we'll come up with an example first. Rounding off. Oh, here they talk about finding sigma. Wait, here's an example. So it turns out that if you don't know sigma, which is probably going to be the case, then there's several ways to come up with a sigma. One way is this range rule of thumb business that we had. We had this a while ago. Remember I told you the range was kind of a pointless statistic to talk about the variation? Well, it could be used if you take care of any outliers and make sure that they're not too involved. You can find the range of values. The range, remember, is the distance between the smallest and largest value. And if you cut that into 4 pieces, then you can assume that each of those, the length of those 4 pieces would be your standard deviation. So that's one way to estimate a standard deviation. Another way to estimate a standard deviation, not very practical, is to do a small study And based on your study, you're going to get a standard deviation, and so you'll use that for your study. I don't know if I would do that. I mean, that means I'm going to do a study anyways, and so you're going to do a study to find S, and then figure out your sample size, and then you'll do another study with a more appropriate sample size. I don't know about that. And then the other thing is that you can rely on somebody else's study that they've done in the past and use that sigma, which if the pass is way past 1997, you probably don't want to use that. So these are possible ways to find a value for sigma so that you can use that formula. Just to accompany this for the visual people, if you take your minimum and maximum values and then you break this up to 4 different pieces, then you can kind of assume that each of those 4 pieces would be a good approximation length for sigma. That would probably be my best bet, is to assume what you think the largest value and what the smallest value would be, and then based on that, create my range and then do the range rule of thumb. Here's an example. They give the answer already. I thought this was going to be a piece-by-piece thing, PowerPoint, but we want to estimate the mean IQ score for all statistics professors in the country. How many statistics professors must we randomly select for IQ test if we want to be 95% confident, and we want the sample mean to be within 2 IQ points of the population mean? Assume that the standard deviation is 15. So remember the things that we need for a formula, if you have the formula written down somewhere. The formula is z sub alpha over 2 times sigma divided by your margin of error, and all this is going to be squared. So we want 3 things out of this word problem. We better get 2 at least, and in the third one we can try to figure out the third one if it's not given to us. But the 3 things is a confidence level. With a 95% confidence, you need to figure out your critical value, which for us, we've been doing this all night, right? 95 is 1.96. You need to know your margin of error. So usually, I don't remember what the wording was for the last margin of error problem that we did. I think they said, literally, margin of error or an error that's not more than, or something like that. Or here in this case, they want something to be within something. 4 percentage points. So these are some of the key words that you would be looking for so that you can associate the number that you get out of this to be the margin of error. So within 2 IQ points, so that's going to be your E. So based on this, 95% confidence, that's probably going to give you your z sub alpha over 2 to be 1.96. Within 2 IQ points, this is your margin of error. So they didn't say percentage, right? So we didn't have to convert this to a decimal or anything like that. Just 2, literally the number 2. And then if they didn't give us sigma, then we have to find it one way or another based on those other ways to try to find sigma. Here they gave us sigma, so problem solved, no big deal. All right. So we got 1.96 for your z sub alpha over 2. You got sigma is 15. You got your margin of error is 2. So this just goes all in your calculator. And if you type it in like as it is, which is a parentheses, 1.96 times 15 divided by 2, close parentheses, and then take it to the second power, you'll get 216.09. But remember the round off rule, is always round up. Always round up. Regardless, this is a 0.9. It looks like I'm really tempted to just say 216, but we want to round up to 217. So it turns out that a simple random sample will need 217 statistics professors from, I guess this is from all over the country, to figure out their IQ scores. What do you think it is? Supposedly, the IQ scores have, for the general population, IQ scores have a mean of 100 and a standard deviation of 15, which is probably why they use this standard deviation of 15 here. So the general population IQ score is 100. Statistics professors would be about what? 103. 96, I don't know. Okay. Any questions? All right, so we have a lot of different types of problems here to do. All right, let's going on to the next section over here. The next section is going to assume that we're still going to look for the mean, so we're going to use a lot of the same formulas, except we're going to assume that we don't know the population standard deviation, which is going to be the more likely scenario in a real life situation. You're not going to know what it is. So the hard part about this section is that we're going to get introduced to a new distribution. The easy part about this section is just going to be another calculator command for us. All right. So, assuming that we don't know the population standard deviation, we can't use the standard normal distribution anymore. So we have to go to another distribution, and the new distribution that we're going to discuss is called the T distribution. It's named after a guy's student. It's not actually his real name. That's his pen name. His pen name. His real name is Gossett, and he was a statistician that worked for Guinness back in the day, and he didn't want his name to be in the study, so he had to use his pen name student. So he came up with this T distribution. What? Irish people, they don't want to stand out so much. So Mr. Gossett made up this T distribution, which is very similar to the Z distribution, but it has some extra parameters over there. It relied on what we're going to call the degrees of freedom, some degrees of freedom. We're going to get introduced to degrees of freedom here. So the less requirements, the more, usually the less requirements, the more difficult your situation is going to be. And here we definitely have very few requirements, aside from a sample being simple and random, and we want to come from a normally distributed population. We're going to use a student T distribution. Instead of the Z distribution, which is what we've been using all along. We've been using the Z distribution all along, but now we're going to use a student T distribution. So less requirement, more complicated. So the complication is going to happen when we start talking about degrees of freedom, and really, you know, in the old days when they had to study this T distribution, and since they had to come from tables and approximations and stuff like that, it becomes really bogged down. And so, fortunately for us with the calculators, we're not going to dwell too much on that stuff. This is not the definition of the student T distribution. Definition of student T distribution is way more complicated than this. Actually, just to waste some time here, let's see if we can find the student t distribution defined appropriately. You know, the standard normal distribution was that complicated e to the some power divided by pi, and I don't know if you remember that, but there was a formula that came up. As you can see, it kind of like mimics the bell curve, and that's a good thing. But then they have all these other things. So this is the CDF is probably what we, PDF is what we would be looking for. This is a PDF. So it's a little bit more complicated. It requires this thing called the gamma function, right? The gamma function, gamma of, and this is actually a Greek letter, it's mu, it's not v, it's mu, plus 1 divided by 2, and then there's square root of this, blah, 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 blah. And this is raised to a power. The hard part about this is that it requires a degree of freedom, and a degree of freedom the degree of freedom gives you a different shape every time. So yeah, I just want to show you how complicated the distribution would actually look like. And there's this hypergeometric function. What is that? Who cares? Anyways, it's some complicated. Maybe I should take a picture of this and put it. Nah. It's a lot more complicated than this. Here they try to make it really simple looking. And what this is really is a transformation. It's like, if you look at this, it looks very familiar to this z-score that we did a while ago. And so instead of actually defining the student t distribution with some complicated thing that would scare you away, they just say, oh, let's just say t is equal to this, and this is how t would be related with the x values. And so now that we're using a distribution called a t distribution, instead of a z sub alpha over 2, our notation now is going to shift to a t. So this is, we're going to use critical, we're going to find critical values, and the critical values will be labeled for us, will be labeled t sub alpha over 2. How many people have an 83? 83. So depending on how old your 83 is, well, hopefully it'll still have the command that we need for this. If it doesn't, then you guys will have to use the table. Table A3, which is not a bad table. It's easier than the table A2 business, but we'll see. Now, the definition of the student t distribution had that mu, that V letter, V-looking letter, and that is defined to be the degrees of freedom. So the number of degrees of freedom for the sample that you would have collected for your study is going to be defined by n minus 1. So n is your sample size. N minus 1 is going to be your degrees of freedom. And we'll usually write df for the degrees of freedom. And you'll see df a lot from now on, because this isn't the only strange distribution that we're going to study. We're also, right after this in the next section, we're going to study another distribution. We're going to get introduced to another distribution that's also going to require degrees of freedom. Okay, so for now, let's say our df is going to be equal to this. So the DF, by the way, this whole business about the degrees of freedom will help find the critical value T sub alpha over 2. Okay, we've been dealing with confidence intervals and stuff like that. We know that the X bar is our best point estimate for the mean mu. Here we're looking for the mean where we don't know the standard deviation. So the only difference between this, well, I guess there's a couple of differences. The differences between this and the last one we did is that, first of all, instead of a critical value of Z sub alpha over 2, we would have a critical value of T sub alpha over 2. And finding that is going to be our new challenge. And then instead of sigma, where we used sigma before, we're going to use the sample standard deviation S. So those are the two things that you'll see change from the margin of error formula from before to the margin of error formula now. So compare it with when sigma is known. We have E is equal to Z sub alpha over 2 times sigma over square root of n. So it's essentially the same except for those two differences. And the two differences are in the critical value and the standard deviation. All right, now they say table A3 has a list of critical values, and each critical value is dependent on sigma. So you're doing a problem, one problem has a sample size of 30, and you can have a critical value for that. Now you're doing another problem, and then your new problem has a sample size of 12. And so now you're going to have a different critical value. You know, with the Z, if I say 95%, you say 1.96, right? Always. For the T distribution, if I say 95%, you have to say, well, what's your sample size? Because your sample size is going to determine your degrees of freedom, and your critical value is based on your degrees of freedom. So, we still haven't talked about finding T, but same formula, right? This is the only difference now. But it's X bar plus or minus E. It's the same thing that we've seen. And then we're still using mu because it's still, this is still all about the population. Population mean. All right, when are we actually going to have to find the critical value? I think I needed three. So table A3 is this table over here, and the tricky part about this is trying to figure out what the area to the left or area to the right is, and then from there trying to figure out your critical values. Or from there, try to figure out your degrees of freedom, and then you finally get to find your critical value. So I just want to have this table ready when we start taking a look at our problem. So here it says a study found this same problem, right? Except now we're going to go do it for reals without assuming that your mean or your standard deviation for the population is 0.62, because it's not. This is a standard deviation for your sample. So this is a case where we would say, okay, I'm finding the estimate for the mean, and I don't know what the population standard deviation is. So let's see what we can find. We know, that's too much information. We know that the mean, and by mean I mean x bar, the sample mean is 98.2. We know that the sample standard deviation is 62, and then we know that the sample size is n. And so, okay, that's fine. We know all that stuff. And we also know that we want to be in 95% confidence. We want it in 95% confidence. So what we're going to need to do is we're going to need to look for this in the table. And this is the same bell-shaped curve that we have, except technically it's a little bit different. It's a little bit different because it's not the standard normal distribution anymore. It's actually the t distribution. And this is a t distribution for n is equal to 106. So we have n is equal to 106, but more importantly, our df is equal to 105, one less. And since we want to be 95% confident, then the unshaded region here is 95%, which means the tails get split in half. What is the percentage in here? 0.025. Okay? So these are the things that we're going to look for in our table. So let's take a look at our table. Kind of small. Lost it. So the first thing we want to look at, well, there's a couple of things we can look at. The first thing I'd want you to look at is that whenever you're doing confidence intervals, we're always looking for the area and two tails. The other thing to look at is your degrees of freedom. So area and two tails, let's see. I think I'm going to need to take a copy of this. Copy and paste it onto So what we want to look at is with our alpha, or with our 95% confidence, and we know this is 0.025, 0.025. So we could take a look at this in one of two ways. We can either take a look at this as the area in one tail as 0.025, or we can look at this, the area in two tails put together, alpha is 0.05. So in two tails, we would look at it as 0.05. If we look at one tail at a time, it's 0.025. Is that confusing? It is exactly the same thing, right? So what I'd like to do is that when we're doing confidence intervals, I'd like you to think about confidence intervals as something with two tails. This whole business with one tail comes up later on when we're doing hypothesis tests. But for now, I think it's always good to just look at it as a two tail, and then you're looking at this number 0.05. Okay? It's the tail and the tail. So if you're adding the two tails together, that's a good way to remember. So you would be looking at your value in this column. The second thing to look at is your degrees of freedom. So with the degrees of freedom 105, they don't have 105 here. So they don't have 105. Our n is equal to 106. Our df then would be 105. So they don't have 105. The best we could do is just round off to as close to the number as we can get. So we'll go with 100 here. And so we follow this through here and follow this through in the middle. So it looks like our critical value should be this number, 1 point. So we'll call it T sub alpha over 2, our critical value, 1.984. Okay. Any questions? All right, now let's take out our calculator and we'll see which of you TI-83 people have this or don't have this command. And if you don't have this, then you're going to have to use a table for the test. So let us go to distributions. This is a distribution. So second function, distribution. And for me, and for all of us, I think the first one's normal PDF, and then normal CDF, and then inverse norm, right? Now, if you go one more, you have inverse T. How many do not have that? Oh, what a bummer. The other thing you could do is that if you have time, go see Frank. Frank has a special function for you. Yeah, so he'll connect his calculator with your calculator, and once he does that, then all you have to do is press some special functions to get the same number that we'd be getting. All right? For the rest of you, inverse T. Now, just like the inverse norm, it's going to be the area to the left. Maybe I should go back here and take snapshots of this as I go along. So let me start a new page here for the notes. So the inverse norm was looking for the area to the left. So the inverse T is going to look for the same thing. So inverse T, it's going to ask for the area to the left. But it's gonna, you know how the inverse norm asks for the mean and standard deviation, and here the second thing it's going to ask for is the degrees of freedom. So if we look at our problem that we were doing, we got two shaded regions here. This, by the way, I don't know if I told you, was 0. It's just like the standard normal distribution, 0, except the standard deviation is all different. And then this area is 0.025, and this area is 0.025. So there's two ways to do this. Like before, I can put 0.025 in my inverse t function and then put it in my degrees of freedom, and then I'm going to get a negative number. Or I can figure out the area to the left of this number and put that area into the inverse t function, then I'll get the positive number. So for the sake of matching up with the table, let's use our degrees of freedom to be 100. It's really 105, right? But we're going to use 100. So area to the left, 0.025, and then comma, my degrees of freedom that I'm going to use is 100. And let's see what happens. Now, what was it before? Using the table, 1.984, 1.9839. So that's pretty good. Except, you know, I got a negative number, right? And I just want to make sure that you understand that whenever you're dealing with critical values, you always want it to be positive. So that is a negative number, and if I were to put, what is it, 0.975 or something like that, then I'll get that positive number. I want to try something else. Instead of 100, I'll put 105, and I'll see what the difference is. And we'll see that when you get up that high, the differences isn't going to be very big anymore. This is fairly close. Rounding off to 3 decimal places, we're going to have different answers. Round off to 3 decimal places here, I get 1.984. Round off to 3 decimal places here, I get 1.983. So it's a little bit off by that much, by a thousandth. But it's close enough, I think, in terms of the problems you guys will be doing. And based on what we have in the table and what we don't have in the table. Yeah?
So does that mean like my math class, that highlights a little option? Or are you just going to keep?
Well, let's just say when you get up that high, I think they'll be looking for, they'll be flexible with the answer. When you're down lower, you know, your answers are very different from 30 to 31. But, you know, going from 100 to 200, your jumps are a little bit bigger. So let's just say when you get up to 100s and stuff like that, let's try to remember that the table goes 100, 200, 300, 400, 500 instead of all those numbers in between. And then try to go with that. Usually when they ask for just the critical t-values, they would be asking for the t-values up here. So that would be easier to correct. And when they're asking for, when they give you larger sample sizes, then they won't ask for the t-values, they just ask for the confidence interval. Yeah, just put 100. Well, try to put 105, try to put in that value. They should be flexible with that because the calculator is more precise than the table. So they should take in the more precise value. But if you get it wrong, then, you know, try 100. 200 or whatever. So our t-value here based on this is 1.984 or 1.983. Okay. So either case, we get the critical t-value. So let's go back to the presentation and have this, have the PowerPoint slides figure out the rest of the work for us. So this is from table A3 that we got. This is our critical t-value. And then you just plug it into the formula. You get something that's a little bit less than 0.12 that we had before. We had 0.12 before, right? Now this is refining it a little bit so we get a little bit more precise value. And then the answers are almost the same. If you remember back, we got 98.08, 98.32. It is the same, huh? So we get the same answers. So how would you actually do this in the calculator? You can actually do this in the calculator without having to figure out what your critical t-value is. So let's redo the same problem. So let's suppose this is our problem, and then we just want to bust it out with a calculator. So let's take our calculator, and guess where we're going to go? Confidence interval. Stat. Tests. Now the one before that we went to the z interval. This time we're going to go to the t interval. So t interval, and go ahead and press enter. It's going to ask for the same things. We have statistics on this. We have our mean. We have our standard deviation is 0.62. Notice our mean was already there, right? That was kind of cool. Our sample size is also there. And then when you ask it to calculate, it's going to take a little bit longer because it has to figure out that t distribution business, which wasn't an easy thing to do, apparently. So let's calculate it. And then we got our results, which is, again, very similar to, or exactly the same as what they had. And you would write your results with an inequality, 98.08, less than mu, less than 98.32. And then you would also write it in words. Okay? All right. So that was easy. Here's some properties for the t distribution. It's not that big of a deal for us, but I think it's important to just kind of remember to note. The t distribution has different sample sizes. It has actually a different curve for each one, but the curves all look alike. They still all pretty much are like bell-shaped. And so when you just draw it, you just draw it like you would do a bell-shaped curve, and then you just mark it a little bit differently. T-distribution has the same symmetric bell shape, but it's actually a little bit wider. The standard normal distribution has a mean of 0, just like the normal, the student T-distribution has the same mean. Excuse me, the standard deviation varies for the different sample sizes. And here's a really cool thing, is that as a sample size gets bigger for the student T-distribution, it becomes closer and closer to the standard normal distribution. And so here are some pictures of some student T-distribution. The normal distribution is supposed to be in blue here, up on top. The student T-distribution for different values of degrees of freedom would be different, slightly. So what I did want to show you is that table again. Since you guys got 95% as 1.96 memorized, you guys have that memorized? 95% would be 2 tails, 5% in the middle, right? So this is the thing. Look at the very last number down in the bottom. So the very last number down in the bottom are actually Z values, critical Z values. They say large, they just say this is large, so this is going to approximate the standard normal distribution. So I never really liked table A2, but if you're relying on tables to find critical values, you still won't need table A2, because you can just look at this table A3, the T distribution table, and look at when it's large. Because when it's large, the T distribution is basically the Z distribution. Just wanted to show you that. All right. Choosing the appropriate distribution, it turns out that it's really based on whether you know sigma or not. If you know sigma, then you use the Z distribution. If you don't know sigma, then you use the T distribution. All this other stuff over here, non-parametric or bootstrapping method, that's stuff that we're not going to cover, so we don't need to worry about that. Assume sigma is equal to something, then you get to use the Z distribution. That's really the only big thing. They have another example here, but we're running out of time, and there's one more section that we're not going to get through tonight. I thought we were going to fly through this and start chapter 8, but I do want this in your records, in your heads, because the next homework is due on Monday, I think, isn't it? So I'll have to make a little lecture on this. You don't have to listen to my lecture. You can just read on your own. That's fine. But just to provide something, I'll make a little lecture on this section on how to do these problems. And unfortunately for these problems, we don't have a calculator command already set in. So we're going to have to do a lot of these things by hand, unless you go see Frank. If you see Frank, then there are programs that would help you do this, that would find the answers for you a lot quicker. Okay? All right, it is 9:30 on the dot right now. So we're done. Have a good 4th of July. Look for that video sometime this weekend, and hopefully I'll get the exams to you by Tuesday.